Hello class, so for this video, we'll be solving this problem. So a box of mass 2 kilograms is pulled up a ramp that makes an angle of 15 degrees to the horizontal, with a constant force of 8 newtons. The box starts from rest and travels a distance of 0.50 meters in 3.8 seconds. So find the acceleration, component of weight of the box parallel to the ramp, magnitude of frictional force on the box, and the coefficient of dynamic friction. So first, let's write down or list the given quantities in this problem. So the problem tells us that the mass of this box is 2 kilograms. The angle that the ramp makes with the horizontal surface is 15 degrees. So it's inclined by 15 degrees. So let's denote that as theta equals 15 degrees. Vi, or the initial velocity of this box, is equal to 0 meters per second. So basically it means that it's at rest. This quantity is 0 meters per second. Then delta x, which is the displacement of this box, is 0.50 meters. So it's a displacement that the box makes in 3.8 seconds from where it was pulled with a force of 8 newtons. So what's required? The required is acceleration. We have to find the acceleration. So let's start with this. So we will use the kinematic equation, which relates the displacement of an object to its initial velocity, vi, the time it takes to reach that displacement, and the acceleration, which its acceleration, and of course the time. So the delta x equals vit plus 1/2 at squared. Since the initial velocity is zero, or in other words, the box starts at rest, then this quantity right here simply becomes zero, which leaves us with this. So delta x, or the displacement of the box during 3.8 seconds, is simply equal to 1/2 times its acceleration times its time squared. So if we multiply both sides by 2, so the 1/2 gets cancelled. So we're left with 2 times delta x equals at squared. So if we divide both sides by t squared, we simply get the acceleration, which is equal to 2 delta x over t squared. But since we know delta x, we know 3.8 squared, we know the time, which is 3.8 seconds, then we can simply plug in these quantities into our equation right here. So we have 2 times 0.50 over 3.8 squared. So this gives us an acceleration of 0.069 meters per second squared. So that is the resulting acceleration of the box when a constant force of 8 newtons is applied, which when the box is pulled up. So that's the resulting acceleration, which results in that displacement at this particular time. So that is the acceleration of the box. So we're going to add this quantity, the acceleration of 0.069 meters per second squared, into our list of known quantities. Now, let's move on to the next part of the problem, which asks us to find the component of the weight of the box that is parallel to the ramp. So this is the next required to find. Since we're being asked to find the weight, then we should analyze, or this is related to the force, is related to the force that is being applied on this particular box. So in this case, we should draw a free body diagram. So remember that the purpose of, or the reason why we draw a free body diagram, is that we want to analyze the forces that are involved or that is being exerted on a particular object. So considering that this is our figure right here, so this is the box with a mass of 2 kilograms. It's on top of this inclined ramp. It's being pulled with a force of 8 newtons. So given these conditions, let's list down the forces that act on this box. So first, let's start with the most obvious force that acts on the box, which is the weight or the gravitational force that the Earth exerts on the box. So let's call this W equals mg. So this is the weight of the box. Then the purple arrow, which is given by this is the normal force that the ramp or the gray or this gray triangle, the ramp exerts on the box. So let's call it N or the normal force. So let's draw this yellow line. Let's make it aligned with the normal force. So we'll see later why this yellow line is here. Then let's draw a similar yellow dashed line. But this time, let's draw it perpendicular. Let's make it perpendicular to the one we drew previously. So given that we have these two dashed lines, and we can see that they're perpendicular to each other, let's pretend that these two yellow dashed lines represent the x-axis and the y-axis. So it may seem strange that our coordinate axes are oriented this way, but you'll see later why this is actually a convenient choice. So we'll discuss that in a while. So let's take note that the angle or the ramp makes an angle of 15 degrees with the horizontal, which is the reason why it's inclined in the first place, or looks like a ramp. Then let's take a note of this green dashed line right here. So from the box, let's draw a green dashed line with an arrowhead. So this black or this the weight vector, which is this given by this black arrow, and the green arrow right here, the green dashed arrow right here, they make an angle with each other, right? That angle is actually theta, which is 15 degrees. So why is it 15 degrees? So let's view this figure in another way, okay? So again, this is our angle, right? Okay, so let's pretend that this ramp, let's redraw the ramp. So this is our ramp right here. Again, the ramp is 15 degrees, right? The ramp is 15 degrees. Now, we have the box that's here. Let's say that that's our 2 kilogram box, and then this is the weight, right? This is the let's treat this as the weight, W, and then aligned with the normal force. So I'm basically just redrawing the figure like a sketch. The normal force. Again, we drew uh, the yellow dashed line, which aligns with the normal force. Then along that yellow dashed line, we draw this green dashed arrow right here. Okay. So actually, let me make it better. Let me draw it as a green line. So let me draw it this way. So it should be aligned with the normal force. So this should do. Okay. Now, why is the angle that the weight or this black vector makes with this green dashed line equal to theta? So let's use what we learned from geometry. So let's take a snapshot of this portion right here of the figure, or basically this one, this triangle, and this triangle right here. Okay, so let's zoom in a bit. Okay, so let's write that again. Let's redraw that figure. So, okay, let's let me redraw that again. So this is the inclined ramp. Then we have this triangle right here. So this portion of the triangle, this portion, that's the weight. That's part of the weight. Then this one, that's the green arrow. So it's basically this, and this, or when we draw it, this and this. So this is capturing this portion of the triangle right here. So again, what angle is this? This is 15 degrees. Then notice that this black, uh, the weight or the weight vector, it's perpendicular to the base of the triangle, right? We can see that it's perpendicular because it's a weight. The weight is always perpendicular to the surface, or in this case, because it's inclined, we will consider the base of the triangle, and that's perpendicular. So this angle is 90 degrees, okay? This is 90 degrees. So what do you remember from your geometry about triangles? Remember that for any triangle, so for any triangle, the sum of all the angles, or the sum of the all of the interior angles, is always 180 degrees. So this is for a regular triangle, okay? Regular triangle. So remember this this theorem from geometry. So if two of the angles are 15 degrees and 90 degrees, then what is this angle right here? That angle right there is simply 180 minus 15 plus 90 degrees, which gives us 75 degrees, okay? So this angle right here is 75 degrees. So if we apply that here, okay, let's apply that here. This is 70, this is 90 degrees, and this is 75, okay? So this is 75, this is 90, this is 15. Now, let's uh let's extend this, let's try to extend this a bit, because in the original diagram, so we have this triangle, we have this triangle, we have this, but we have this, which is basically the ramp. So let's extend it just a bit. So this line, this is a line, okay? This ramp right here. And what is the angle of a line? Or basically, if we have a line, what is the angle if we uh, start from this point and end to this point or any point? It's always 180 degrees, right? So if uh, if we know that this is 75 degrees, this is the angle that we're trying to verify that it's 15 degrees. What is this angle right here? Well, if we look back at what we drew, we noted that this green arrow aligns with the normal force. It aligns with the y-axis. And what did we say about the normal force? The normal force that a surface exerts on an object. So the normal force exerted by a surface is always perpendicular to the surface itself. So if this ramp right here is the surface, this is the normal force, then this normal force is perpendicular to the surface itself. So if we extend this normal force as what we did with a y-axis, then this green arrow right here, which are collinear or align altogether, then this green arrow right here should also be perpendicular to the ramp itself. So what does that mean? It means that this angle should be 90 degrees as well. 90 degrees is 90 degrees as well. So it turns out this is 90 degrees. But what is familiar about this angle? We have 75, we have 90 degrees. We said that a line, if we have a line, the angle that is created is 180 degrees. We have two of those angles, this part, and this part, 75 and 90. We have this triangle right here, this triangle right here, which has three of its angles given, 15, 90, and 75. If a line also has an angle of 180 degrees, similar to a triangle, then we can conclude that this angle right here, or the theta, is also 15 degrees as well. Because if a line has an angle of 180 degrees, then if we add this angle of 75, this unknown angle, and this 90-degree angle, and we should get 180. But based on our calculations, that is 15 degrees because these two angles are also the same angles that are involved in this triangle. And notice what is their third angle? It's also 15 degrees. So that is why the angle that the weight force vector, the angle that the weight force vector the angle that the weight force vector uh, that is created with the green dashed line is also theta, or 15 degrees. So that is the reason why that angle right there, it was denoted as 15 degrees. It's the same angle as the angle of the incline. Okay, so that is the reason why. Okay, so we know that is theta. What else do we know about this free body diagram? We have this. The green dashed line is mg cosine theta. So because we know that this angle right here is also theta, then this green dashed line is mg cosine theta. So let's do a bit of trigonometry now. So toa. Let's redraw this triangle right here. So this is the, actually let me make it straight. So this is the weight force vector. This is the weight force vector, the green dashed line, the green dashed line. And for the sake of argument, let's add a generic color just to connect this so that it's a triangle. Okay. Now this is a right triangle. This is a right triangle right here. So that is 90 degrees. So this is the weight. So let's find what this green line represents. So using SOHCAHTOA, if we take the cosine of this angle, which is this one, then we're simply finding the ratio between the adjacent side, which is this side right here. Let's call that x for the meantime, x, and its hypotenuse, which is w or mg, since weight is equal to mass times gravity. Then we find that x is simply equal to mg cosine theta, or in other words, we can express this as mg cosine theta. So that is the reason why this green dashed line is equal to mg cosine theta. We simply used trigonometry. Now, for the blue line, since we've drawn that here in our sketched triangle, then let's also solve for that. So it's mg sine theta, and the reason for that is if we take sine theta, or the sine of this angle in the triangle, we have opposite over hypotenuse, so that is the weight. Uh, I know that is the actually no, it's not m. Sorry about that. The opposite of this theta right here is this side, or the blue one. Let's call that y. Then the hypotenuse is also the same. It's mg, or the weight. So we find that y is equal to mg sine theta. Or in other words, this side right here is mg sine theta. So using trigonometry, we were able to represent or quantify the magnitude of these vectors, the green dashed line, green dashed arrow, and the blue dashed arrow, which are mg cosine theta and mg sine theta, respectively. But notice that this blue arrow right here, we can actually move that to here. Okay, so let's see how that works. We can remove that blue arrow and place that here. But why can we do that? Okay, why are we doing this in the first place? We solved for this triangle, so that means that this blue arrow should be right here. Why are we doing this? Why are we moving it? Well, if we take a look at what's happening here, we're solving for this triangle, right? We found mg cosine theta and mg sine theta, which is the blue arrow. But how did it transfer from here? Well, note that This right triangle should be the same as if we drew the green arrow right here and the blue arrow right here. This is the same right triangle. Again, this is if we do this, it looks like a rectangle, right? Well, my sketch is not straight, but if this were to be, if we were to transfer mg cosine to this one or duplicate it, we find that we have a rectangle. So if we have a rectangle, we have similar triangles, which means that this angle right here is also going to be theta. And if that angle is also going to be theta, then using trigonometric ratios, we should also find that this green arrow is also mg cosine theta, and this blue arrow right here is mg cosine theta. So how did it transfer there? Again, this blue arrow right here, which is originally here, is also the same as this. But since we have, since this is a free body diagram, this arrow simply represents the y component of the weight. This is the reason why the box objects in a ramp sometimes they move down. It's because the force of gravity is still acting, but not in the way that we think. It's not going down, but it's going in this way. It's because the y component of the weight is the one that causes things in an inclined ramp such as this one to fall. The x component of the weight, which is mg cosine theta, is the one that balances out with the normal force. This is why we don't see the objects in a ramp to sink within the ramp or to jump. Okay, it's the n and mg cosine are the ones that work in an opposing manner. The y component of the weight is what causes things in a ramp to slide down. Okay, so that is why we're able to transfer this blue arrow from here to here in order to represent the y component of the weight that causes this ramp or things in a ramp to slide down. So we have mg sine theta. Okay, let me just erase some of that. So going back, so the weight, we decomposed it into its x and y components, the blue arrow and the green arrow. Okay. Now, referring back to the question, we want to find the component of the weight of the box that is parallel to the ramp. Again, what is that weight? Looking at this free body diagram, the ramp is the hypotenuse of this triangle right here. So parallel to it is simply the y component of the weight, which is mg sine theta. So let me correct myself. I mentioned the x and y components. At this point, please ignore what I said. Whenever we're considering the weight of an object in an inclined ramp, there's no x and y components, okay? Or the x and y components can change depending on our theta. In this case, the mg cosine theta appears to be the y component of our weight because we oriented our coordinate system this way. And the x component of the weight is our mg sine theta. So let me make that correction right there. In order to not be confused, let's just denote the mg sine theta as the parallel component of the weight to the ramp and the mg cosine theta to be the perpendicular component of the weight to the ramp. So the component of the weight that is parallel to the ramp is simply equal to mg sine theta, or the blue arrow. So the mass is 2 kilograms, so from our given quantities. The gravity, which is g, that's always 9.8 sine 15 degrees. That's from the theta right here, sine theta, which is 15 degrees. So if we calculate that, that gives us 5.07 newtons. So the answer, or the component of weight of the box that is parallel to the ramp, is simply equal to 5.07 newtons. Okay. Now, for the third For the third quantity that we need to find, that is the friction force on the box, or given by this variable f fric. Okay, so let's find the friction force on the box. So remember that the frictional force, this is the force that is exerted by a surface on an object when a particular object is moving. So it always opposes that motion. So looking back at our free body diagram, first we noted the normal force and the weight. So that's N, mg sine theta, which is the weight parallel to the ramp, and mg cosine theta, which is the weight perpendicular to the ramp. Now let's consider another force that acts on this object. So again, it's mentioned in the problem that this box, this particular box, is pulled up a ramp with a constant force of 8 newtons. So we have this red arrow right here. That is the force applied to the box, which causes it to be pulled up. Or the person is trying to pull this box up. That's why we have this F applied, which is 8 newtons. Then we have the frictional force that the ramp exerts on the box. Because again, whoever is pulling this box is applying a force of 8 newtons, who is trying to accelerate this box, which causes the box to move. But because the box is expected to move in this direction, or going to the direction of this force, of the of this force applied, the F applied force vector, then the frictional force that the ramp will apply to the object should be opposite to this. So we will, as we saw previously, we will denote that as F fric. So here are the conditions that we need to consider. There is no acceleration on the y-axis, okay? So again, we shifted our coordinate system. It's this slanted coordinate system, but it makes things convenient. Look how the normal force and the mg cosine theta align with the y-axis. Look at how the force applied and the frictional force align with the x-axis, okay? So in the y-axis, we noted that there's no acceleration in the y-axis because in the problem, it doesn't say that the box is jumping or sinking down. It means that there is a zero net external force that is applied on this object, at least in the y-axis. So this is the first condition that we will consider. Thus, again, the summation of the forces in acting in the y-axis is simply equal to zero, which means that it is in equilibrium in the y-axis. Therefore, the summation of Fy, where the net forces acting in the y direction, will not contribute to the overall net force. So again, Newton's first law of motion tell us that for an object to be in equilibrium, or to be at rest or in constant velocity, the net force should be equal to zero. But because Fy will not contribute to the overall net force, F will contribute to the overall net force, we only need to consider the force only index component. So we're going to see if this object is indeed going to accelerate. It's going to accelerate if if summation of F is not zero, okay? So let's establish the equation. So the summation, or the net external force applied to this box right here, at least in the x-axis, is simply equal to applied the applied force, which is 8 newtons, minus uh, the parallel component of the weight that acts on the box, minus the frictional force. So notice that there are two forces that actually oppose the motion of this box. So when you pull something that's on a ramp, the forces that act on it is both the weight and the frictional force. The weight is simply the parallel component of the weight, which is mg sine theta, and the frictional force that the ramp itself exerts on the box. So this is why we have this equation right here. We're adding the force vectors F applied, F friction, and mg sine theta. Then for Fy, since there's no acceleration in the y-axis, then this is simply equal to zero. Now, again, because Fy, the summation of Fy is equal to 0, then we have this. So what is the proof? So remember, class, this is the Pythagorean theorem, the equation that we use when we're trying to find the magnitude of the vector. We find the sum of the squares of its x and y components, find its square root, then we have the magnitude. So in this case, if Fy is 0, then what's going to remain in this equation? Fx squared. But the square root of Fx squared is simply equal to Fx. That is why we have this equation right here. So this is a mathematical proof of why we have this, okay? Now, going back to our equation, so to find the net force that acts on the objects in the x-axis, we simply need to add the force vectors, which is the applied force of 8 newtons, the parallel weight, the parallel component of the weight to the ramp, which is mg sine theta, and the frictional force that the ramp exerts on the box. However, so we have these two equations right here, but how can we find the value of delta F? We simply relate that to the second law of motion, that the net external force that is applied on an object is simply equal to the mass of the object times the resulting acceleration, right? So to find the net external force that is being applied on this object, we simply need to multiply the mass of the object, which is 2 kilograms, and the acceleration of that object, which is 8 newtons, because it says, because problems, based on the problem, it actually gives us the kinematic aspect of the problem, which is how the box moved. So it starts from rest, but then because of the applied constant force of 8 newtons in this direction, the box then accelerates and travels a distance of 0.50 meters in 3.8 seconds. The first part of this problem involves kinematics, which led us to find the acceleration. So this acceleration means that there is indeed a non-zero net external force that is applied on this object, which caused the acceleration in the first place. Now we're going to find it using Newton's second law of motion. So we find that the net external force that is applied on the box is 0.138 newtons. So notice how it is significantly less than the applied force of 8 newtons. So this means that the frictional force that the ramp applies on the box and the weight and the parallel component of the weight to the ramp when combined is actually decreases the applied force by a significant amount, which leads us to this relative, which leads us to this value of 0.138 newtons, which is relatively smaller than the original applied force of 8 newtons. So going back to our equations, since we have established that Fy is simply equal to 0, then this leaves us with this, that the net external force applied to the object is simply equal to the net external force applied to the object in the x-axis. But because we know this, we know the F applied, we know mg sine theta, this is our missing quantity. So again, the applied force, the object, which is the pulling, is 8 newtons. Mg sine theta, as we saw, or the weight, the component of weight of the box parallel to the ramp is 5.07 newtons. So we find that if we add the so we find that if we manipulate the equation by adding the frictional force to both sides, then we have this form. So the frictional force that the ramp exerts on the box is simply equal to the applied force of the box, which is 8 newtons, minus the weight, minus the net external force on the box. So this is given by 8 minus 5.07 minus 0.138. So we find that the frictional force that is applied, that the ramp applies in the box in order to oppose that sliding motion in this direction or going up is 2.792 newtons. Okay, so that is the answer for the third part of the problem. So the friction force on the box that the ramp applies is 2.792 newtons. Now, for the last item, we need to find the coefficient of dynamic friction. So let's introduce this concept of dynamic friction. So the friction force in physics, it's defined to be this, okay? So on top of what we've learned from frictional force, it opposes the motion of the object. We can actually go deeper. So the frictional force is actually related by this equation right here. It's equal to the coefficient of the dynamic friction times the normal force. So what does this mean? It means that the frictional force is particularly dependent to this variable, which is what we call mu k. So it's pronounced as mu k, mu, which is a Greek letter, mu k. Okay, that's how we pronounce it, mu k, or to pronounce it better, it's mu k. Yeah, okay. So mu k is the coefficient of the dynamic friction. This value varies per material. So each material, such as wood, glass, mu k is different. However, for the N, which is the normal force, that is simply the force that the surface exerts on the object. And this is uh, most of the time equal to the weight of the object, assuming that the object uh, is not accelerating in the y-axis. So that is the frictional force. It can be quantified by the coefficient of dynamic friction. Particularly, the coefficient of dynamic friction. This is obtained experimentally, meaning uh, if we perform different experiments on different materials, we can actually uh, find a value for this mu k, which is simply a unitless value. Okay. So using this equation, knowing that we know that the magnitude of the frictional force on the box is 2.792 newtons, in order in order to find the coefficient of dynamic friction, we get the value of n using one of the established equations. So we know that the net force in the y-axis is simply equal to 0, which gives us this equation right here, n minus mg cosine theta from our free body diagram. So 0 equals n minus mg cosine theta. So we just rewrote the equation in another way. We put the 0 in the left side and n minus mg cosine theta in the right side. Okay. So we find that n equals mg cosine theta. So if we transpose mg cosine theta to this side or add mg cosine theta to both sides, we have this. N equals mg cosine theta, which is from what I said previously, that in most problems, the normal force is equal to the weight. Okay. Or in this particular problem, since it's an inclined ramp, mg cosine theta is the component of the weight that is perpendicular to the surface. So plugging in the given quantities, the mass of the object is 2 kilograms, the gravity is 9.8, we have cosine 15 degrees, which gives us 18.9 newtons. So the normal force that the ramp exerts on the object is 18.9 newtons. Okay, so we have this. So given our equation that the frictional force is equal to the coefficient of the dynamic friction of the object or the ramp times the normal force that the ramp exerts on the object. So we find that mu k is simply equal to the frictional force over the normal force that the ramp applies on the object. So we have 2.792, which is already given, and the normal force of 18.9 newtons. So notice that the quantity of 2.79 newtons is in newtons, right? That's a frictional force. Normal force is 18.9 newtons. Notice that the newtons cancel out, which give us 0.15. This is why I said that the coefficient of dynamic friction is a unitless quantity. It has no units. So based on our calculation, the coefficient of the dynamic friction is 0.15 newtons. So notice how the problem builds up to the final one. So we need to solve the problem chronologically. From the acceleration, we found the component of the weight of the box parallel to the ramp, the magnitude of the frictional force on the box, and the coefficient of dynamic friction. So most problems in Newton's law of motion, it's solved chronologically. you need one particular quantity in order to move on to solve for the other quantities. So this is how we solve this particular problem. Example D1, inclined plane with kinetic friction.